this video we are going to discuss about the solution of the harmonic equation of the harmonic oscillator. We already discussed about the harmonic oscillator in a previous video, but today we are going to discuss about the solution of the equation. So the equation of the harmonic oscillator is the following. Okay, so here basically we have a differential equation in which our function is x and x is a function of time, a function of t. So here we have the second order derivative with respect to time, and then we have a linear term with x and omega 0 squared, where omega 0 is somehow linked to the frequency, linked to the period of the function of the solution. So we are going to find the solution of this equation resorting to the complex numbers. So the idea here is to consider a function x of time defined as a complex function e, where e is raised to the power of lambda times t. So we have our variable t, which multiplies lambda, and lambda is a complex number, so lambda has a real part and an imaginary part. So we basically are considering an exponential function, so that we basically, if we consider the second order derivative of that function, we basically get the same function multiplied by lambda squared. So here the idea is to consider an exponential function, so that we have a second order derivative which is proportional to the function itself. In fact, if we put basically this function in this equation, lambda squared times e lambda t plus omega 0 e lambda t equal to 0, where basically we calculated the second order derivative here of the function x, so the second order derivative of the exponential function. Okay, so now the idea is to consider the fact that if this is true, then we can write that lambda squared plus omega 0 squared is equal to 0. And now here we basically have two imaginary solutions. In fact, the solutions of this equation are lambda, let's say lambda plus, for example, which is I times omega 0, and then we have lambda, let's call it lambda minus, which will be minus I times omega 0. Okay, so we basically found the solutions of this simple equation, which are two imaginary solutions. So if we put these two terms in our function x, we will get two which will be simply e raised to the power of I times omega 0, and then we get x minus function of time e raised to the power of minus I omega 0. So these two solutions, x plus and x minus, are complex solutions. So these are two complex numbers and are independent. So that means that the general solution of our equation, of the harmonic equation, will be a combination of these two functions. So we can write the general solution x function of time as a1 x plus function of time plus a2 x minus function of time. So this is the general solution of the harmonic equation, and now we are going to look for, we have to basically find the real solutions, because we are interested in the real solutions of the equation. So if we have x, the general solution is x, we can choose two different, we can choose the values of a1 and a2. So the first values of a1 and 2 will be a1 equal to 1 over 2 times I, and a2 equal to minus 1 over 2 times I. Okay, so if we take a1 and a2 defined as these, defined in this way, we will get that x, the general solution, will be 1 over 2i x plus minus 1 over 2i x minus. So that means that we get 1 over 2i, and x plus was e raised to the power of I omega 0t, and I just realized that here I forgot t and t, obviously, because x plus and minus are functions of time. And then here we will get 1 over 2i minus 1 over 2i e raised to the power of minus I omega 0 times t. Okay, but we can also write these two functions considering the cosine and the sine functions, because we know that, for example, e raised to the power of I omega 0 and t will be cosine of omega 0 t plus I sine of omega 0 t, and similarly we get cosine of minus omega 0 t plus I sine of omega minus omega 0 t. Okay, so we know that cosine of minus omega 0 t is equal to cosine of omega 0 t. So since here we have minus, these two terms basically cancel. And here we have also that the sine of minus omega 0 t is equal to minus sine of omega 0 t. So since here again we have minus, basically we can sum this term and this term. So here we will get we finally get just sine of omega 0t. Okay, so this means that if we choose a1 and a2, as we chose here a1 and a2, a1 as 1 over 2i and a2 as minus 1 over 2i, we get that the general solution is sine of omega 0t, which is a real solution. Okay, so now if we choose, if we take a1 equal to a2 equal to 1/2, then we know that x of t, so the general solution of the equation, will be 1/2 x plus 1/2 x minus. Okay, so here, as we said, we would get this okay, so that means as we did previously, we can write these two terms using cosine and sine. So we get cosine plus I times sine, and then here we get cosine of minus omega 0t plus I sine of minus omega 0t. Okay, so here again we can consider the fact that cosine of minus omega 0t is equal to this term, and this term is equal to minus this term. So that means that since here we have plus, we can cancel these two terms, and we can sum these two terms. So we get 1/2 times 2 times cosine of omega 0t. The solution, the general solution of the equation this time is cosine of omega 0t, which again is obviously a real solution. So we basically found that the general solution is can be sine of omega 0t, and we also found that another solution, another real solution, is cosine of omega 0t. But these two solutions are independent, so that means that the general real solution will be a function x of t that is a combination of sine and cosine. So we have to write a1, so the first coefficient, times sine of omega 0t plus a2 cosine of omega 0t. So here basically we wrote that the general solution is a combination of this function and this function, and this means that this is the general real solution of the harmonic oscillator. Okay, so now consider the fact that for any values of a1 and a2, so we can write that for any a1 and a2, we can find an amplitude a and a phase v, such that a1 is a times cosine of v, and a2 is a times sine of v. Okay, so we basically write this so that cosine of phi and a sine of phi here in this solution. If we do so, we basically get that x of t is a cosine of phi sine of omega 0 t plus a sine of phi cosine of omega 0 t. Okay, but we can also write that since here we have cosine sine plus sine cosine, here basically we can write that the solution is